All right, so hi everyone. My name is Stanley, and this is my colleague Petr. So we're going to take you guys through this tutorial today. I hope it's going to be very, very useful. So just a quick word of warning. We're going to actually do a lot of hands-on exercises. So we want you guys to follow through and to go through the exercises with us. So please put up your hand if you're stuck somewhere. We have two of our colleagues here that's going to help you. That's Donald and that's Wei Yu. So they're going to try and, if you guys run behind, just to come and help you if you don't follow or is something that you're just stuck with. So please put up your hand and don't be scared to ask questions. We do want you to follow through in all the exercises. So let's go to the first slide. So a quick disclaimer here. So we're all four actually work for Barclays, and so all the views expressed here is not necessarily the views of Barclays. It's all of our own content, even though we're using their representation format. All right, so quick introduction. So that's our links to LinkedIn. So Stanley van der Merwe and then Petr Wolf. So just a bit of my experience. I've been a data scientist for about 10 years now with Barclays, developing statistical models on the retail side. We predominantly actually used SAS for our model development, and most of my experience was with SAS. And there was a decision by our management a few years ago to change over to Python and fully just use Python. So today we're only just using Python, which is good. We have a bit of legacy SAS code left, but we basically just everything is transferred to Python, which is a good journey for us. So I have about 2 years experience with Python. And then Petr here, who's on my left, he's actually the opposite. He's very experienced with Python. He's part of the QA team as well. So QA is quantitative analytics in Barclays. And he's been actually very instrumental in that process of us switching over to Python. And then just quickly, the slides, all of these slides, you don't have to take pictures. You can just find them on the GitHub link. And also for code and setup, we'll go through that in the presentation, but we'll have this link on PyData NYC 2019 to GitHub. It's below every slide as well. You'll see we've put it there. So we want you just to follow through those. There's like a README on how to get set up. We'll go through that now. So let's jump to the next slide. So just the abstract. I think all of you would have read this coming to the tutorial. So a quick summary is, normally just think of it. When you start writing new code, there's a few things that we actually put right at the end of the priority list. Normally those are reproducibility, how you structure your code, and also just the runtime performance of your code. And what that does is it actually has an impact on the successful implementation of your code or for the continued use of your code, and also the maintenance cost in terms of time and money when you do that. So what we're trying to do in this tutorial is we're going to highlight some steps that we think will improve your code and improve its shelf-life, and also actually hopefully will lead to others wanting to take your code, replicate, and build on top of that. So that's what we're trying to do with this tutorial today. So what you'll learn is you'll see that you'll learn how to structure your code into composable, reusable blocks. And then we'll jump into the first thing would be intake, using intake. And to do that, to replace boilerplate code for data loading. And then we'll also start looking at testing and also like code quality. And they will look specifically at PyTest. If we have some time towards the end of the presentation, we'll look at hypothesis. And then also PyLent, and then we'll look at performance by using profilers, and then once we've identified bottlenecks in your code, we'd want to try and show you what type of tools like Numba you could use to make it faster. So just in terms of show of hands, who actually has used things like, who's used intake before? Like just show of hands. All right. And in terms of PyTest, has anyone used PyTest before? Okay, good. And what about hypothesis for testing? Okay, one. And then PyLent, have you used any of that before for code quality? All right, and then just any type of like profilers, line profiler or profiler. All right, and then the last one, Numba. Has anyone used Numba? All right, good. So I think you're going to learn a lot based on that. So let's jump into the next slide quickly. So just in terms of who this tutorial is for, so it would be for people, and that's why I actually asked for showing of your hands, would be, this is once you've started getting into Python, but you want to take the next step in trying to improve your skill set. And if you predominantly use Jupyter Notebooks and you want to actually move and step away from that, or actually use this in conjunction with the other tools we're going to teach you. And also, if you're similar to me, you've moved over from a certain code base that you've used to using and you came to Python now, and some of the best practices you can use, we want to try and highlight today. This might not be necessarily a good tutorial for you if you're very, very experienced with writing modular and testable code, and also if you're very, very experienced in automated testing and code optimization. So in terms of what we're going to cover today, there's about 7 basic or main steps we're going to look at. Firstly, on the right, you'll see here is a typical modeling notebook. So please, again, that's part of my disclaimer now, don't use this modeling notebook for your modeling purposes. It's really, really basic and actually shows you how not to do things. So, but we're going to start with that and then build on top of that and see how we can improve it. And then we'll just quickly jump into setup first. Then we'll go to reproducibility, data sourcing, testing, and then we'll look into code quality and performance. And after each of these sections, what we'll do is we'll do a summary just to make sure we cement the ideas we're trying to convey. All right. So quickly, these are our pictures that we had. They were all Barclays approved pictures. So what we're going to try and do is we're going to show you, instead of, we want to show you the bad, which is like represented by the cupcakes here. And then we want to show you, instead of doing the bad, let's do the better, which would be like using the fruit and the vegetables there. So what we'll do at every step in those 7 steps I mentioned is we'll do a brief explanation. I'll do that. And then we'll do a quick demo. And then we'll ask you to do and follow through with hands-on exercises. And you'll see with this, we're actually going to repeat things like almost 4 or 5 times. And the reason for that is we found that that's how people actually learn. You want to really cement the idea. First, let's plant the seed, and then we're going to actually go through step by step, get you some experience, and we're going to do a summary and recap at the end. So I think just if you go to the next slide, you'll see we'll do a sample solution once you've had some time with the exercise yourself, and then we'll do a summary and recap to make sure we highlight the key points. All right, so out of scope today would be these points here. Version control, continuous integration, peer review, documentation, and automated data validation. These things are really, really important. I just want to tell you, just bring attention to that. They are very important, and with the tools we're going to highlight today, you have to use them all in conjunction to actually get a really good code base. What we've done is we've left some links at the bottom of each slide, which is some good reading. These two links we actually read through, and that was the premise for our discussion today. A lot of that came out of these 2 links. So I would encourage you to go and read a bit more about this if you in your own time. Okay, so let's jump to the setup. So actually, Petr, do you want me to hand over here, or do we? Yeah. So Petr will take you quickly through the setup. And as I mentioned, would be if you're struggling with the setup, just put up your hand, and our 2 colleagues there would also help you.
So hi everyone. Thanks for coming. So hopefully the setup is actually easy. If you've done it already on your computer, you're all set, I hope. If you have not done the setup yet, you can use the binder link that's either on the slides or also on the GitHub homepage. That will take you right into a browser interface where you can interact with our notebooks. If you do prefer to run this on your computer, it will take you 5 to 10 minutes to set it up using the instructions again on GitHub. So are there people who are having issues setting things up? If you do, just raise your hand. Donald or you will come by. We can at this point just switch to the notebook.
You have to escape.
Yeah. So you have 2 options. If you're on our GitHub, you can either press this link, or you can do these steps of the local installation. If you have not done, I would recommend you go with the binder link, which will open in a new window. It will take a minute, but it should drop you right into a tutorial page that looks like this. So can we just get a quick check on whether people are set up? If you could raise your hand if you're all set, and you can see something like this in front of you, either locally or on GitHub. Looks good. So I can see a lot of hands, but not everyone has raised your hand. So we're going to continue with the tutorial. But if you do get stuck, please let us know and someone will stop by and help you out. It's important so that everyone is set up. Otherwise, this tutorial will not be very useful for you.
All right, so let's just bring up the slides again. So you'll see there's a few exercises. We're mainly going to use Jupyter Notebooks throughout the tutorial, but just a few notes on tooling. So you'll see that there are a few .py files in the exercises, and we're actually going to edit those and save them and then run them again. So if you just look at the instructions here, so if you see any .py file, Peter will take you through that, but you'll click on that file and then you'll edit it and just save it with some of the as part of the exercises. So it's here in step 1 and 2, it just shows you how to do that. And the second thing we'll do is we'll also use the terminal. So and this is actually optional, so you can go into Jupyter Notebooks, say new terminal, and we'll use that for some of the testing exercises. It's just actually the benefit of this is you're going to run it in the terminal and you'll get some nice colors that shows red, you failed your test, or green, you've not failed your test. Otherwise, you can also use some special Jupyter magics. You can use the percentage or the exclamation mark, which Petr will also show you how to use that later on. Okay, so let's go to the next slide. So our first point would be reproducibility. So what do you think of if you think of reproducibility? So a quick definition for this would be a reproducible data science project is one that allows other people to actually go and recreate what you've done and build upon that. So that's what I would say is a good definition. So you allow others to use your code, reuse it, or modify it. And why would we actually want to focus on reproducibility? Well, a few key points we've highlighted here is, I think most in your jobs as well, it will be similar that normally things start off as a one-off analysis. And then once you find that this is actually a good analysis, you want to repeat this. So when that happens, you don't want to go back and try and re-understand your code from scratch again. You actually want to be able to use that code and put it either in production later on or be able to run it very quickly. The second point also, if you're in a modeling environment where you do like data science and you build predictive models, you would want to recalibrate these models, maintain them, and also monitor them. And as part of this as well, you don't want to go and, if you have to recalibrate, say, quarterly, or you have to go and do some maintenance, you don't want to go and figure out, oh, where did I save this data? Why did I do this thing here? Why do I have this huge function that has like several hundred inputs? So you would actually ask yourself these questions, and those questions would just go away if you write reproducible code. And then the next 2 points would be that projects actually do promote knowledge sharing. So if you have a reproducible project, just think about if I send you a notebook and it's very all over the place, it's not really well constructed, I don't have any comments in there, I don't have any tests written, would you actually spend the time to try and read through this and understand this thing? I don't think that answer would be yes. It would be, you would actually then just move that away and try and write something out of your own. So it promotes knowledge sharing if you have something that's very, very easily understandable and to follow as well. So that's the third point. And then the last one would be you might want to move your projects to production. So when you think of production, there's normally 3 things that pop up. The first one is your code, does it have tests, well-written tests? That's the first question. The second one would be, is your code, is it actually optimized for performance? So that will be your second question. And then the third thing would be, do you have code quality? So there's some standards that you have to follow for code quality. Is your code of a high enough quality that it can move to production? And we're actually going to touch on all 3 of these points in today's tutorial. All right, so let's move to the next slide.
All right. So in our first exercise, we're going to open a notebook in the exercises folder called 01 reproducibility. You can get there by clicking in the tutorial in the exercises folder. I'm going to do that just in a second. We're going to use some slightly unusual commands in that notebook to check what Python packages which we've installed, what version of Python we're running. I'm going to try digging a little bit deeper to also look what version of the operating system we're running on. Why that's important? Packages change, computer systems change, things evolve, things that work today may not work in a month's time, things that work on your computer may not work on other people's computers, things that work in development may not work in production for various reasons. So these are things that are actually very important to keep in mind and have some control over. If you went yesterday to the great Netflix talk on reproducibility, you would have learned actually much more on that. We're just going to focus on one particular aspect of reproducibility here, which is the various versions of packages. So I'm going to switch quickly into a notebook. So if you're set up, you can just follow into the exercises folder and open the first one. Let me make that bigger. And so everyone should at this point be following with us. You can have this in front of you and you can run these commands with me. So everyone's using in pandas, right? But if you do that, you can also check a special attribute of pandas called __ version. A lot of libraries have that, not all. But if you want to know what version of pandas you're actually using right now on your computer or in your environment, this will give you the answer. And if you follow the instructions or you're running on Binder, you should actually see exactly the same as we do. If you're seeing a different number, you have a different version of pandas, you may actually struggle with the tutorial. There are special commands in Python that you can use to list all packages. I'm going to use one here, pip freeze. The exclamation mark here, if you're not used to that, is a way in Jupyter to execute system commands. We alluded earlier that you can do the same in the terminal. If you prefer using terminal, and you're comfortable doing that, you can switch to using terminal. But for the purposes of the tutorial, I think we're going to stay in Jupyter all the time. Pip freeze lists all the packages. Why is this important? You may want to save this as a byproduct metadata of your analysis so that you can later recreate the same environment, or at least know what versions you've used. Similarly, if you're using conda for packaging, depending on how you installed it, conda list will give you a similar output. But you can dig deeper. You can actually wonder what version of Python you're running, and that also changes. So that would be in the sys module. Here we're on Python 3.6. That's actually relatively old. There's Python 3.7, now even Python 3.8 just came out very recently. And with every release, there are breaking changes, there are differences in behavior, differences in numerical results you may get. So all of this is important to understand. Finally, the operating system that we're running on can also be inspected from the Python platform module. And so now everyone will probably get something slightly different depending on where you're running. It will be either Windows, Linux, Mac OS. If you're running in Binder, it's going to be some virtual Linux platform. There's some more useful things from the platform module, like what processor you're running, what architecture, 32-bit, 64-bit, etc. And if you're kind of losing track and thinking this does not matter, there's an article you can read that just recently came out. It was an episode of Python Bytes podcast that talks about it, where a tiny difference in the platform actually caused a big difference in a lot of scientific papers because of slightly different behavior of a certain function on one version of an operating system versus another. And this got accumulated because it was in a shared utility that got copied over into many projects and used in hundreds of scientific papers. And so details can matter. Before we move on, I would just check in with you if everyone is following the tutorials, if anyone's having any troubles running things. This was basically a warm-up, nothing really difficult or groundbreaking here, but just a check-in with everyone. If you're not set up by now, not able to run these cells, let us know. Someone will stop by and help out. And with that, I'll hand it over.
All right, looks like everyone's up and running. So what we'll do next is just jump into our next exercise, or just give an intro to that first. And that will be, or actually, let me just quickly finish with the review, like I promised. So, so why does reproducibility matter? A few things we've mentioned now is, or we haven't mentioned explicitly, but that is important, is it's for collaboration purposes. You want people to reuse what you've created, and also for maintenance purposes, like I mentioned. If you have a model, you have to recalibrate that, or you have to maintain that. You want that to be reproducible. Ways of making your project more reproducible is actually something that we've just done here. You have to explicitly make sure that people know what their dependencies are and also the requirements. And this can be done in one of two ways. You can do it with the requirements.txt file in the root directory, which we've put on our GitHub repository, and also with a getting started guide, a getting started guide in your README file would also help. And then three other points here, which we're actually going to touch on some of them here in the presentation. But the one that's out of scope, like we mentioned, is version control. But we just want to bring your attention back to that again. It's very, very important that you do version control. So just to back up your code base, firstly, it helps with collaboration, like I mentioned at the top. And also it helps with tracking any changes to your code base. So then the third point here was also actually you should to make sure your code is trustworthy, and people trust it much more if there are written tests, well-written tests that you can run to your code base. And then the last thing is actually this forces you almost to make your code reproducible. If you work with a big team of people, multiple people on multiple environments, this actually forces you to start getting your project in a reproducible manner. So that's the fourth point. And then again, here we have some very, very useful links that you can go and read more about reproducibility. I want to actually bring your attention just to the third bullet point, which is Talk Python episode 227. I would actually encourage you to go and listen to that one Sunday afternoon if you have some time. It's very, very good stuff to listen to. And they have some good links to papers there as well. So let's go to the next point. So now we're getting to data sourcing as promised. So a few things. So you know that there's quite a bit of time and effort that goes into defining data and also loading data when we start working on projects. So as a data scientist or as someone that wants to use data, there's actually just three basic things you want to know. You want to know what type of data is available. You want to know what format it's available in, and how do I get my hands on this data so I can start doing an analysis. And also one thing that's very, very frustrating with dealing with data is the amounts of boilerplate code you'll need to use to try and get your hands on the data. So that brings us to this library or this package called Intake. And what Intake does, it provides a very, very simple but very useful split between the data users, so the data scientists, and also the maintainers of data, the data source catalogs, which would be the data engineers or your team that provides data. So what this does, it provides the freedom and the flexibility to these data engineer teams to go and decide whether they want to store your data, in what format do they want to store it, and also what packages they want you to use to get your hands on the data. All you actually interested in is getting your hands on a data frame or something like that, and they know that. And this clear split actually helps with setting those guidelines. Then what Intake also does is they have like a consistent approach to organizing the data, and also the commands you have to use to get your hands on the data. You don't want to, every time you use a different data format, you don't want to go and learn a whole new set of commands and tests, things like that. If you just learn like an Intake and you know this is how I get my hands on data, it's much easier and it also saves time. And that's actually done through their data cataloging system. And this provides you with descriptions of the data, some of the arguments you can pass to load the data, and also some arbitrary but very useful metadata that you can use with these catalogs. And we're going to look at a few catalogs as part of the exercises. And then also it also tells you which plugins you're going to use to load the data. So just in terms of the plugins, how do we define a plugin? And this actually comes from the Intake documentation. They actually say that the business of a plugin is to actually move from a certain data format into a container that you're used to working with. So like a Python list or a pandas data frame or a NumPy array or something like that. So that's what a plugin does. It just gets you to that container of the data. And there are some built-in plugins for Intake. Those are like CSV, NumPy, text files, like we mentioned here on the slides. And then we also have some extendables here, Parquet, Spark, S3, and many more, which we created a link for if you guys wanted to go and jump into that. So I think we'll now go into our first actual exercise quickly, and I'll hand over to Petr to do that.
Thank you. So before we jump to the exercise, I wanted to kind of illustrate that problem a little bit more in using this sample notebook that we mentioned at the beginning as the thing that you should not do. If I put it up on screen and we look at this notebook, it illustrates a typical workflow someone might do in model development. We'll go through it step by step, but we began with reproducibility. We talked about how important it is to actually know in what versions we're importing all these packages. And now we're at the data loading part, and what you might see in a lot of code. Actually, I should say the data we're using here is generated dummy data set. It doesn't have any actual value. So again, please don't do any real modeling with it. But it's based on a California housing data set that comes from a really great book, Hands-on Machine Learning, that if you want to know how to do things properly in that space, you should definitely follow, not learn from us. But in terms of the actual implementation, what you often see is, because it's going to be code something like this. So, uncomment on Michael's computer, then there's going to be a path on Michael's computer. Bob will have its own version, which will not work. Then there's going to be some link that no longer works. And then you're going to have a command that loads data. And if they're actually still there, you're lucky. Often you will find that the file is gone and you don't even know where to find it. And that's over, right? At that point, everything else is useless. Here the data is there, I hope, so you should be able to read it and look at the data frame, which has a bunch of columns about housing prices in California. We're going to use that as a toy model. But the point I'm trying to illustrate that this is bad. The parsing actually is also having some issues. And so we're going to try doing something better. We're going to use intake to standardize the way data sets are loaded and share that with others. I'm just going to keep this view for a second. We're going to open the notebook 2. We're going to look at what an intake catalog might look like. We're going to incrementally improve it until it describes the data set correctly. I'm going to try using it, and then there's some optional exercises that you might do if you're running ahead. I'll bring this slide up again, or you can follow on your own using the PDF on GitHub. So again, from the home page, going to exercises, I'm going to open up Notebook 2, and so please follow with me. We're going to import pandas as before. Now we're also going to import intake. And so what intake does, it splits the role of a data provider and a data user. So as someone who's bringing in to your company or for analysis a new data set, you have to go through a lot of pain. You have to find out where the data are, how to parse them, how to understand them. And so intake's not going to take that away. You still have to go through that pain. But what it helps with is that you're now the only person that has to do that, because you can describe this process in a concise way, and then you can share it with others so that other people can really benefit from what you've done and load the data without having to repeat all these mundane and error-prone parsing steps. So an intake catalog is a text file in YAML format. We'll look at it just in a second. This is one that would describe the data set. Again, I'm using a special Jupyter command to list a file. If you wanted to click on it, you want to edit it, we'll do it in a second. You just navigate to it in your Jupyter browser. It has a mandatory header with version. We can ignore that for a second. And then it has a list of data sources. Here we only have one entry in that space called housing. We give it a description. We say it's a CSV file, and we say where it is. That's pretty much all the file currently says. But as such, this file could be shared as a way of standardizing the instructions. Intake can read that file, and the command for that is open catalog. Load it into Python and tell me things about it. It can tell me now what sources I have in that catalog. Obviously, there's just one, the one that we defined. I can access that source and see some of these properties. So the things that we saw above, the CSV format, the description, some of the parameters, you can access it through a dot or through square brackets if you prefer. But most importantly, there's a read method. So once I've defined this and loaded it, I can press read and I get a data frame back. So if someone had done this catalog definition for me as a user, I don't write anything special. I don't even know where the data needs to be. All I do is I press read and I get a data frame, which is kind of the ideal case you want to be at. So the exercises here will now go and edit that catalog to resolve a bunch of issues that we still need to take care of in terms of the parsing. So one issue, if you look at the data, there's a median house value that actually isn't in the right format. It has a comma separator in between thousands and hundreds, which forces pandas to parse it as a string, so we can't really operate on these as numbers. And we need to fix that. In the original notebook, if you scrolled through that, you would see that there's some very complicated code that does that. replacing string comma with an empty string and applying to numeric. That is sometimes what you can see, but in pandas read CSV, there's an option for that, which would be the modern. There's an app for that, because there's an option pretty much for anything in read CSV called thousands. So our first exercise will be, and we can look up that option. Apologies. Let's hide this. We're going to add that option to the catalog under a section called CSV arcs. I'm going to do it for you, and then you can follow with more with other options. So in Jupyter, I'm going to navigate to the home folder, open the data folder, and look at the catalog. As we alluded earlier, this editor opens up this part of Jupyter. It's always going to be available for you. And so I'm going to add a new entry here, which is how intake wants me to enter every additional parameter. And this option is called thousands. And the value is just this comma. So if I save this file, and I go back, just going to try whether this worked. I'm going to open the catalog again, and I'm going to read it right away. And I should see that my median house value is now parsed correctly. I can see actual proper numbers in that column. So try that and follow from this point on. There are a few more exercises for you. There's another issue in the near ocean column. If you scroll at it, you can see that the values are yes or no, or lowercase yes, or lowercase no. And for modeling, that's not very useful. You would want to parse it as ideally 0 or 1s. And again, there's an option for that in pandas read CSV, actually 2 options that you might need to combine. So the exercise for you quickly would be to open the documentation of pandas read CSV. The link is right here. Check out what options might apply in this case, and then try introducing them in your catalog, reloading that catalog, and seeing if you could, if you're seeing the right data. And finally, the third exercise here is to deal with some funny NA representation in the column housing median age, for which again there's an option. So we'll give you just a few minutes to try this out. If you are stuck or you don't know what this is, just raise your hand, and we'll show you a sample solution in just a few minutes.
Is it parsing everything, all columns for commas?
Yes.
So if you had like a text column with commas in it.
Right, that's a good question. Yeah.
It would take those out, right?
So I think if it's a text column with commas, that's fine. But if you had like another numerical column, sorry, the question was, would the 1000 separator apply to text columns? I think it would not apply to text column. It would apply to other numerical columns.
Okay. But it's like, I guess I'm confused because you said it initially was reading that column as text, right? Or as an array.
Yeah, so what pandas does is it tries to guess. Unless you provide that information explicitly, it tries to guess what type each column is. And it was misled by those commas, thinking that this is text. Now you said that there actually is a separator in my numbers that is a comma, and so now it understands that it's a number, and it will parse it as a number. But if you had another column in which you would have some comma-separated words, it would still appear as text, and it would still get parsed as text.
Okay.
Does that make sense?
Why wouldn't it affect that other column?
I think it will try, but if it sees it's still words, it will keep.
Keep it? Okay.
Yes.
Good to know. Sorry, I missed
Go ahead.
the exact syntax.
Oh, sorry, I'm going to flip through that one.
Yeah, just the syntax. Oh, there it is.
You can just open it, just click on it in your, on Jupyter, and then you have to go back to the directory.
It's not quite JSON format.
It's called YAML. It's slightly different.
this argument's only going to impact that data set in the catalog. Is there a way to just set it for like all the data sets in the catalog?
So the question is there a way to set some parameters for all data sets in a catalog? I don't think so, not through this syntax, but there's something called plugins, which would let you do that. So we're going to cover that in a minute.
Why wouldn't I do this for all my data sets in the catalog?
No, intake is awesome.
Just mention to people that there's again they can just go to data and open catalog. There's 2 questions on that.
Yeah.
But just when you didn't realize how to edit it.
I thought maybe it was more like JSON. Sorry.
All right, so I heard some yays. I also see some people struggling. So I'm gonna try to get everyone on the same page by showing you a sample solution. Hopefully you've been able to achieve at least part of that. Again, if you want to edit these files, these are text files. We're going to use the same for other Python files later. You can just in your Jupyter, click, go to the home folder. That's the root of this exercise. If you open a notebook, that's the familiar interface, but you can also click on any other text file or Python file, including this catalog, and edit it right there in the built-in editor. So we saw this catalog in the data folder. I actually have a solution, so anytime you feel like you want to cheat, you can actually jump in there and find all the answers. The one that we're going to look at is this catalog. It contains a little bit more stuff, but I'm going to describe that in a second. So the beginning is the same. We have the metadata, the sources. There's just still this one data source. It's still a CSV file. I've changed the URL to actually, instead of loading it from my computer, to load it from GitHub, which you can do as well. And I'll put in a variable which you can later change if you want to load it from your GitHub repository. So instead of a local file, you can just point to data sets on the internet. Again, catalog that for someone else. So you found this great link, you want to share that with someone else. You attach all these other information to it, and hence it becomes a trivial example. This is the 1000 separator that we talked about. This is the conversion from these 3 lines, actually, or 4, are the conversion from yes or no's to zeros and ones. Again, you would find in Panda's documentation how to do that. And this is another detail that needed to be taken care of to interpret none as an NA. There are additional things you can have in an intake catalog. There are user-facing parameters. So you want to expose some flexibility to the user. That can be done through parameters. Here I expose an attribute called GitHub username with my username as the default, but giving users the flexibility to change that if they so wish. And I'm also defining some plots associated with the data set. So if someone gets this data set from me, they can also run some easy plots that I've defined the parameters of to get a sense of the data right away without having to write a lot of coding. This is optional, but nice. What it looks like together, if I open this notebook in the solutions folder, and I quickly browse through that for you, we've just seen the catalog. If I load that one, and I just do read, you can see I'm providing this username. I do read. That's all I had to do as a user. I loaded a catalog, and I press read. I did not know where the data was, what are the parsing details. I don't need to know any of that. I'm just given a nice clean data frame with all these issues taken care of because someone else had written this down for me. And it's a standard format. that will apply to any other data set. The plotting, that's just a nice feature on top of it. I can now get the housing data set, type .plot, and get a plot out, which again has been customized for this particular data set, so it can be more useful to a user that sees this for the first time. Questions on data sourcing or intake? We will do a quick recap, but we're going to move on to testing right after this. So if you have questions on this part, now would be the best time.
It's a very specific question that may not be as relevant, but if you have a custom data source, this is a bad example, TSV, tab separated value, let's pretend that that wasn't supported built in. Does intake a lot? I know you mentioned plugins, but can you like make your own like?
Yes, so the question was, what if you have a special data source, some format that's not CSV, right? So absolutely, so intake is very extensible. The technique you're looking for is called plugins. And so there's an easy way of writing your own, and there's also an online repository of plugins that people have already written. You can actually look at them. This is the instructions for making a driver. It's called driver sometimes, but that's the same thing. It's actually very very simple if you're used to coding. If you prefer to get this from like an open source project, there's a growing list of plugins that people are written. I've learned about intake last year at this conference from the author, and I got very excited, and then this list has been growing ever since. So I think it's an active community, and you likely actually find your format here. If not, you or someone can write it, put it in this repository, and then anyone can use it. Other questions or comments? So flip back to Stanley. The slides.
All right, great. So just before I give the summary, I think the first point I just want to make is, even if you didn't finish that whole exercise, every exercise doesn't really build on the other one. So you can go and try and do that at home, or just finish it, or look at the solution. So all of our exercises are independent of each other, like a well-written test. Just to quickly summarize about the use of intake. So there are a few benefits of using intake. So the key one is, you can actually just think of this catalog file you have now. You can actually just go and share that over the network now with someone that has the same access as you have, and they can go and use that YAML file we just spoke about, that catalog file, to just go and load the data. So that's a very, very big benefit of going through all of this. And like I said, there is a division between who maintains these catalog files and who uses them. So hopefully, like, your data team would provide you with these catalog files, as long as you just have access. Yes, question?
What's the process of creating catalog files themselves?
So yeah, who's responsible for that, you're saying, or what's the question?
What's the process for creating catalog files? Here we just loaded in catalog files.
Yeah. So the process will be exactly like the exercise almost. You have to almost go and use that YAML format and go and write all of these and provide the URL. If it's something that it's like a company specific, you'll have to provide like parameters like the login details or something like that. So the process would be exactly almost like we tried to show you the YAML format. That's the process of writing it. Yeah. All right. So, and then some of the other benefits quickly, just before we jump into testing. Sorry, Petr. Is this helps you with converting a lot of boilerplate code into reusable catalog files that you can use. It also helps you to load a variety of data formats into something in a container that you are used to working with, like we mentioned, pandas data frame, a Python list, or an NumPy array. And then it also, the catalog files, they describe data sets, and this makes it easy to reuse, and you can also share between projects and people. So those are some of the key benefits we wanted to highlight. So next we jump into testing. So this is a very, very big subject, and you can actually spend this tutorial plus a few weeks on just testing, but we're gonna scratch the surface and show you some really useful things to do in testing. But before we jump into that, how do you know that your code normally works as expected? Just think of it. If you have a problem, what you normally think is, okay, I need to solve this problem, this is the outcome I'm looking for. You're going to write some code, and you just check whether the code produces the output as you would expect. That's normally how we would do it. But how do you make sure that this code actually is still valid later on, once you've done that, and also, say someone else wants to use it? That's where the challenge comes in. It's immensely challenging to make sure that your code remains valid over a period of time. And that brings us to firstly to assertions, and then I'll talk about testing a bit more. So assertions in the code help with checking certain assumptions. So an assertion is simply a statement that checks whether something holds true within a certain part of your code or program. And assertions actually make sure that your data inputs are valid and also your outputs are consistent. So that brings us to testing. There are different types of testing. We mentioned 3 testing types here. So unit testing, integration testing, and regression testing. So unit testing, and we're going to look at unit testing and integration testing now in our exercises. But unit testing is basically testing a single unit of code and checking whether that produces results as expected. And then once you combine these pieces of code to check whether they work correctly together, that's what we call integration testing. And then the last part is regression testing, and that's whether you check whether a system behaves, doesn't change its behavior after you've modified some of its details. So that's what you would call regression testing. And just 2 more definitions I need to provide, because some of the examples we're going to do now will touch on this. So positive versus negative testing. So a positive test is a type of testing on a system where you provide it with valid input data. So you're actually testing whether the application behaves as expected with positive inputs. So that's what we would define a positive test. And a negative test would then be, it's a variation of testing on a system that just, if you provide it with invalid data. So it checks whether your application behaves as expected when provided with negative input data. And what you're actually doing is you're checking whether a program doesn't behave like it shouldn't behave. That's why you want to do negative testing. So we can actually jump into the exercise now, I think. Right.
So again, we're going to look at some bad practices. If I just get organized here. In this notebook, we saw some code here doing stuff that's a little bit hard to read. We can scroll a little bit further and see more code. If someone can tell me what this does, kudos to you. I wrote this, and I still, I probably can't explain what it does. And it actually has bugs as well. What it's supposed to do, as the comment suggests, is there's a column in the data that contains geographic location, latitude, longitude. That turns out to be actually very common. If you attended the keynote on Monday with the squirrel dataset, that has the same column in it. But it has a slightly different format. If you wanted to parse it to get the location of every squirrel in Central Park, you would be doing something like this. But this is difficult to write. It's even more difficult to read. And it has bugs in it that are not actually at all obvious. So what we're going to do instead is we're going to take this code out of the notebook. We're going to put it in a separate file so that we can modularize it, reuse it later, but also that we can test it in isolation. Because as Stanley said, the way I would test it here, I would just run it. I would look at the data. I would not look at all the data. I would look at the first few lines, and I would think, yeah, that's okay. But it's not, as maybe the 4th line actually suggests, it doesn't always work. But if I was lazy, I wouldn't even see that. So let's go again to the homepage, go to exercises, and we're on number 3. I wrote this file for you. You will find it in the same directory. It's called parsing.py. I'm just going to look at it here, but you can open it in the same editor we use for the YAML files. And it defines a Python function. So I'm assuming everyone's comfortable with that. I'm just going to explain very quickly what this does. It takes one argument, the location string. It uses the split function to parse it into the 4 segments. The latitude string, the indicator, whether it's north or south, the longitude string, and then the indicator, whether that's east or west. It then applies some logic to convert those strings to numbers and to use positive or negative number if it's the northern hemisphere or the eastern, etc., which is how these coordinates are defined. And it then returns these 2 numbers, the latitude and the longitude. What it's supposed to do, if I then import it back into my notebook, so from parsing, this is the parsing file, I import parse location, I run it on a string, it doesn't actually work, right? Because there's some bugs. And I could squint at the code for some time, and maybe you already see some issues, but a better way is to actually write a test that will do this testing for me and that I can later automate. So before we fix this issue, we're going to look at one more file in the same directory called test parsing. The file is going to do the same as I did. It will import the parse location, and it defines a special function called test location, which we refer to as unitest. This function does only one thing. It runs an assert, which is a special expression in Python, which will do nothing if the expression is correct, if it's true, but it will fail and it will give me an error if it's not true. So I'm going to assert that the parse location is what I would expect it to be in this case, 3, 4, 5, 6, and 1, 2, 3, 4, 5. And then we're going to use this tool called PyTest that some people have raised their hands, they're familiar with already, to automate this testing. What it looks like is on a command line in a terminal or with an exclamation mark in IPython in Jupyter, I can run PyTest, test parsing. And what I should see is an output that will look like this. It will have some header that we can skip for now that will say it found one test in the test parsing. It's following this naming convention. Everything that begins with the word test will be executed. And it tells me F, it failed. Depending on what console you're running, you might get colored output. It would be red. And it tells me no, 1, which I got, is not equal to 3556 that I was expecting. There's a problem, fix it. So the exercise now for you is to go back to that code in the parsing file, see if you can spot that issue, if you can fix it, and rerun this test, and whether you can make it happy. So the way you can do it is to navigate to this exercise folder and open the parsing file. See if you can see some bugs, fix them. You can go back to your notebook or terminal or rerun the test until it's happy. We'll give it a minute or two, and then we can get around the same page again.
So again, if you're not sure completely what to do, just put up your hand and try and help.
So in the interest of time, I'm just going to ask if anyone found a bug. 2 bugs. Where's the first one?
The obvious one is that you're returning the string.
Yeah.
Yes. So this is one bug, right? And the other bug?
You're not wrapping up the condition for -1 versus +1. So if it doesn't find south, it just returns 1.
That's correct. There's an operator precedence issue because the way Python interprets this is different from how you would actually read it. You want to multiply it by this whole expression, not just the -1. There's actually a third bug. I don't know if anyone can see it.
No, I passed after that.
So there's a bug here. This is -1 on both sides. You only get it if you actually test with both north, east, and west, which the data would actually not have because it's California, right? That's how you would not know. This is fixing the code, but we also need to improve our tests because working with just one sample is not enough. You found some bugs, but not necessarily all. I'm going to jump now to the solutions and show you a little bit more. So I improved the function a little bit. I'm just going to comment on some of those points, but they're not critical right now. I actually went back to using a regular expression, which may not be a good idea. But if I have good tests, then I can be more comfortable about my code. then if I don't have those tests, then I would probably not venture into that space. I've also added a little bit more comments. I've explained what the function does. Also, what you can raise if the location is actually invalid. This is the negative test cases that we want to understand. And I've added a few examples. This is useful for anyone that wants to use that function, or for me later to understand how to use it and what to get, what to expect. Why I'm showing it here, because I can get double value from doing this. This can also be tested. Turns out that PyTest can also see these types of comments and validate that they're actually true. In my function, and we don't have to go through that code very much, I just rewrote that logic a little bit, but I also added a error message that will be raised if the location is not valid, and I will write tests to make sure that that does happen in the cases where I would expect it. You may have, if you had the time, which you probably didn't because we're running this pretty quickly, you could have tried different locations. In PyTest, if you want to save yourself some typing, there is a tool called parameterize where you can extract these different test cases into like a little list and then just repeat the same. Instead of writing these lines 10 times, you repeat them basically. You could imagine this is like a slightly better for loop. But I'm just enumerating these test cases, but I'm trying like the north and south pole and different combinations and just making sure that it will always work. I then also define these negative test cases. So how about strings that are just not correct? Will the function return something, or will it raise the correct expected exception? And for that, I'm using this PyTest raises tool that is part of PyTest. So this was the test file. If I run that again, hopefully this will now work. It found these many tests. Each dot is a test. And I have now a good outcome from PyTest telling me that 12 tests passed. I have confidence in my code. I can share it. And someone using this code can trust that it actually will work. If you've been to a tutorial and I've heard it multiple times, people say, I created this open source package. It has 100% code coverage. And it's claim to fame then, because claim to fame, you can claim that all your code or your lines of code actually have tests written for them, so people can trust your package and people use that to advertise their the code quality of their products. The one thing I wanted to highlight at the very end is this option to PyTest, that if you add, it will actually run these examples from your documentation as tests, and it will verify whether that's true or not. That's very useful if you write documentation for others, you put examples there, you want to make sure those examples are correct. Well, this tool will verify that for you. So if I run this again, it will actually find one additional test in the parsing file. Note that this is not the test parsing, this is the actual source code file, and it verified that as well. Questions for testing? We're again going to do a quick recap, and we're going to move on to code quality and then performance. If you have a question on testing, on using PyTest, or in general, please ask.
I always get the unit part of the unit test confusing. So how large or small is a unit?
So the question is, what does unit in the word unit test actually refer to? And I think people would probably give you very different answers.
Oh, okay.
I think the rule of thumb is that it should match to like one function or like one aspect of functionality. Right? It's easier to test things one at a time rather than test some very large, complicated workflow in which many things can go wrong. Right? Your test will be simpler if the thing you're testing is simple. Here we're just testing, simple input, simple output. So a unit typically means a single function or a single operation.
Okay, so if a unit, say you have a for loop with 3 if-then cases, so are each one of the cases a unit?
Right. Okay, so the unit would be that for loop, but you would write multiple test cases to explore the different code paths that you can get into,
okay.
right? Or different test cases, right? So like in here, right, you would write inputs that explore the different situations your code can get into, so that all that code is exercised. That's how you achieve that 100% code coverage. You actually create situations in which all parts of the code get executed.
All right, just a quick recap then on testing. So firstly, we mentioned this a few times, but test-driven code does build trust. Like Petr also mentioned, when people write packages, they actually do say I have full coverage or not. So that builds trust. It also maintains validity of code over time. So as people start making changes to your code base, they can just rerun the tests and make sure that everything is still valid. And then also testing encourages programmers to better design their programs as well, and also to write it in a testable manner. What that means is you create self-contained almost functions and classes that can more or less run independently of one another. And that actually helps. This way of designing code and this way of looking at code helps your code to be more understandable and reusable. So that's the quick summary of testing. And then also, there was a talk today just before lunch at PyData in New York by Rahul about, it was more advanced testing, but he actually covered all of these aspects. He also looked at doc test, hypothesis, which we'll hopefully look at later on, and PyTest. So I think if you didn't attend that talk, maybe look that up later on. And that goes into a bit more advanced testing. So let's go to the next part. So now we jump to code quality. So just ask yourself the question, how does one improve code quality? So the answer would be by modularizing, reusing, and also by making code more readable. So firstly, when you say modularizing, what do we mean by that? That means when you write like short single-purpose functions with very, very well defined inputs and outputs. So you should always modularize code rather than copying and pasting code. So if you see a piece of code where you repeat the same thing a few times, like a few if statements, or a few things that you repeat, you know that your code quality is not up to standard. So you want to try and modularize that. Modularizing code allows others to understand or to remember its functionality in a single mental chunk. So what that means is people can actually go and understand the functionality of this function, and that helps also with understandability of code. And this also, a side effect of modularizing code is it leads to more readable, reusable, and testable code as well. And you should always decompose your programs into functions. And a rule of thumb is not to have too many input parameters. I think a rule of thumb would be to have 5 to 6 input parameters, and also don't reference outside information in your functions. And the main motivation for this is you want your functions and everything to fit into the most limited memory, short-term memory of all, and that's the human memory, short-term memory. So you want to try and keep it into small pieces. If you see this code, like it's hundreds of lines of code, and trying to solve something, it's very, very difficult to follow through, or to follow. You should always reuse code instead of trying to rewrite it. There's a lot of well-defined problems out there that people have solved with very, very well written libraries and packages. So rather use that than trying to solve or write your own routine to solve problems. And also, as you would see actually some of the functions that Petr writes, you should always explain your function with a doc string or so that explains it in words what you're trying to do and achieve here. Then the second to last point will be you should always give your functions and variables well-defined and meaningful names. That helps to document the purpose of your functions, and also it makes your code more readable. And all of what I've said now is actually quite subjective. You could go into a debate of, hey, my code quality is quite good. You have to indent like 3 or 4 times, and you have to do your doc commentary this way or so forth. So we'd encourage you to use tools to evaluate and ultimately check for known issues. Then to try and have this debate will also save you quite a bit of time. So we can actually now jump into an exercise with, I believe we'll use Pylint to try and check code quality.
So, as Stanley said, this tutorial is mostly about tools, right? And you could debate endlessly which code is better, and everyone thinks their code is the best. So there are luckily tools that can bring some objectivity to this, and also automation to highlight and find some of these issues. So I'm going to jump out of presentation, and as you can guess by now, we're going to use the number 4 exercise. So Jupyter exercise is number 4. This one is short, so we're just going to do it together. I'm going to walk you through that. This blob of text is basically what we just concluded and leads to this introduction of a tool called Pylint. There are many similar tools. This is one one of the best though, that similar to PyTest can look at your code, but instead of running it, it will scan through that code and highlight some of issues that it thinks exist in your code. And these are defined as rules in that. So I'm going to try doing this on this parsing function that we just used, and let's see what comes out. So I'm going to say exclamation pylint parsing.py. And it gives me an output that looks like this. It gives me a file name and the line, so line 8, the character, if that matters, and then it complains about some things. So it's actually very pedantic. It complains even about extra spaces at the ends of lines. That's maybe not that useful, but it also can complain about missing module docstring. So as Stanley said, it's good to document where your modules and functions are for. If you don't do that, this tool can highlight that. It tells me that I'm not using the variable longitude, which actually was one of the bugs. I was accidentally using the longitude string, not the longitude, and this tool would have told me if I looked at it. It's also telling me that I have an import OS that I'm not using. So this code was pretty short, but it still highlighted some issues. If I don't want to deal with trailing whitespace errors, I can disable them either in the code or on the command line using a parameter -- disable. And rerun again. Now I'm getting a slightly more useful output. I'm also getting a score at the end. So these are all metrics you can apply to your code base and watch over time to see how you're doing. If you write a lot of functions, you can pay attention to this and see if the quality is kind of overall deteriorating. And what are the issues. There are also different classes of issues, C for convention, W for warning. For really serious problems, you would have an error. So in the interest of time, we've already fixed those issues. So we're going to jump to the last exercise, which is to look at some really bad code. So I'm just going to put it up on the screen for a minute. And just look at it and count for yourself what issues you would highlight on this code if a colleague of yours gave it to you to run without further explanation. Would you understand what the code does? Would you see any bugs in it, or would you know what it's for? I can actually see there's a typo here, so I'm just going to fix it real quick. Wondering how we got it in there. So this does not need to be reflected upon very long. You know, the code is not very meaningful. It's not very clear what it does, and it seems to be not quite logical. Anyway, and there's some bugs in it. But just in your own head, see if you can spot some, and we're going to compare that to the output of Pylint to see what it would tell us. So I'm just going to run it on this bad code and see if it's useful. So it's complaining that we don't have a docstring. It's also complaining about the naming foo, right? It's like a popular name. If you don't know how to name something in programming, you name it foo, but it doesn't really help. That's the same people naming data frames df. How do you know what's in it, right? Just by the name. So it has a list, a blacklist of names that it looks for, and if you use them, it will complain. It has some more pedantic conventions about argument names. Also, UV may not necessarily be the best name. There's a missing docstring. It's telling me that I don't need to have an else if I'm returning. Again, that's an option. You know, that's an optional thing you can turn off if you don't like. But more important is complaining about the fact that I'm not being consistent in that function. I'm in one branch returning, in the other one just printing something that the function doesn't really behave in any consistent way. And finally, there's an error which is highlighting a bug in the code. It says too many positional arguments for function call. If you look at the line 15, that's this line where I'm calling the function foo with 3 arguments, but it's defined with 2, right? So this will actually break. And without running the code, Pylint is smart enough to tell me that. So it understands your code, it has some predefined patterns that it looks for, and is generally a useful tool to have to validate your code on top of the tests that you should write. And I got a score of -11 out of 10, so congratulations to me. See if you can do better. That is code quality. I'm going to do a quick recap and move to the last section. We're doing okay on time, but if anyone has questions, now would be a good time to ask.
Okay. Yeah. All right. Quickly on on the recap, actually, just it's not too much to recap about here, but there are, if you want to go and look at this, I think it would be useful to go and actually look at Pyland and also use the options that Petr mentioned to disable some of the information you'll get. And then also we've provided some links to other types of tools that might be very useful to use under the See Also section. So let's jump over to performance now. So with performance, and I think this is very, very useful too, especially if you're struggling with a bit of performance. The first golden rule, firstly, is before you actually try and optimize your code for performance, you should always make sure it works first, right? So that's the first thing. Otherwise, it will be quite frustrating to try and optimize performance. So the most productive way to make your code fast is first to check whether it does as expected. And then the next question you should ask yourself is it actually worth spending the time to optimize my code? And then once you've determined, yes, it is, I want to optimize my code, you should use tools like Profiler or Line Profiler to determine where your code is actually spending time. And in terms of that also, what area might be worth optimizing. Once you've determined that, which we'll show you how to do, then you can actually go and use some of the pre-built, like I mentioned earlier as well, pre-built functions that's out there or packages that's out there that's already optimized for performance, like NumPy, Pandas, and SciPy, to try and see if you can make your code faster. Once you've done that, then, so the second to last one would actually do also when you do any operations on rows, that's actually not a good thing. You should try and always do operations across columns, which will speed up your code. And then the last one would be, once you've done all of this, you've tried to optimize the code itself, then you can use something like Numba to compile code in hotspots. So we're going to show you all of these now using Profiler, how to identify bottlenecks, then make some changes using these built-in methods, and then at the end of the day, just show you also how we can use Numba.
So this is the last exercise, and also maybe the most complex. So whenever you get stuck, please raise your hand, someone will stop by, or ask your questions right away, and we'll address it directly. We're going to use actually multiple tools now, but hopefully it will still make sense. So before I jump to the notebooks, I'm just going to illustrate where we're coming from to give you a little bit of the background. In the sample notebook, if you continue with this workflow, we've parsed some data, we looked at it, we decided that we want to build a model. So we prepared the data, nothing spectacular going on there. We create some additional features, we put in a const column, we train a linear model on this. It's obviously a very bad model, don't do this, don't use it. We look at its result, but reason I'm going through this is then we get to some custom code. I've written a function here that evaluates the root mean square error as a way of measuring the performance, and I didn't listen to Stanley, so I did it row by row, which is going to be very slow. I didn't use any optimization. On a small data set, it may not matter, which is then okay, but on a large data set, this could actually be a productivity killer, and so we want to see if we can do better with this code. Right? It calculates the RMSE, but other than that, it's not a very performant code, and we'll get in a second into why that is. I have some additional code here that we can get to in an optional exercise, but first, let's together jump into the exercises. So 0.5 performance, and I'm going to preload one additional thing, Line Profiler. I'm going to get to what that means later on, but that's just for the setup. As a recap, this is the definition. Again, it's obligatory to put a math formula on the slides. Should give it, and that show that we're legit. This is it. There's not much more than that.
Is it formatted using LaTeX?
Yeah, LaTeX. Of course, you can see that we're advanced. Yeah. This is the function, and I'm just going to measure how it runs, right? And this is kind of the sequence in which you would typically go. Here we don't care about the numbers. I'm just going to generate some random data so that I can measure the performance in something sizable. I'm going to have 1 million random numbers in 2 different columns. One would be, in this case, the predicted, the other one would be the actual, but it doesn't really matter. What I'm interested in is the time, not the answer. So there's a magic command in Jupyter called %time. If I put it in front of any expression, it's going to measure the time it takes to execute that line. There's a multi-line version, %time, that you would use to measure larger blocks. So everyone will now get a slightly different number, on my computer, actually this is Stanley's computer, it took 1.4 seconds. And you should see something in that order, right? And now I have to make the first choice. Is this too much? Is this too little? Does this matter? If it's 1.4 seconds and I'm just going to run it once, it doesn't matter. But if it's something that gets called very often, or it came out as 15 minutes, then I want to probably continue. However, it's not always that accurate. If I do it again, I might get a slightly different answer, because things in computers fluctuate a little bit. Sometimes the first time you run something, it's faster or slower. So there's another one which is slightly better. It's called time it. What it's going to do is going to run your code multiple times and then give you the average. So if you want to time some code, this is actually a better version. It takes a little bit longer because it's running it multiple times, but it's going to give me an overall statistic about the code. So here I'm looking at 1.36 seconds plus or minus 85 milliseconds. I have a better idea about that code. So let's say I've determined that this is too much. I need this code to go faster because it's in some critical portion of my code base. So how can I figure out what's wrong with it? There are two tools that we're going to look at. They're called profilers, and they are going to measure where the time is actually being spent. This 1.3 seconds, where is that going? So the first one is a built-in profiler. It comes with Python, and it has a magic called prun for profiler run, which I'm going to do on this function. And I'm going to get an output that breaks it down by function. In this case, it's not super useful. If I squinted it, I can kind of see that there's this square root that's with a bunch of zeros, so it's not actually taking much time. I can see my RMSE function here taking most of the time. In a code where lots of functions are involved, this will be more useful. In this case, we're not really getting much insights from this alone. So we're going to use another tool, the so-called line profiler. And as you can guess from the name, it's going to give me a line-by-line information. So if I do that again, it's going to run my code again, but it's going to trace per line where the time is being spent. And now you can have your code on the right-hand side and the timing on the left, and it gives you a much better idea. So you can see that 78% or this many, I guess, milliseconds are spent on this line, 21% on the iteration. So most of the work is actually on this line, 21% here. And so if I were to optimize this is how I would go about it. These would be the focal points of my optimization. So how can we optimize? Operating on lots of data in Python is typically slow if you do it on a line-by-line basis. So what you want to do is to leverage libraries that can do it faster. So the first thing I would reach for is to actually use NumPy, since I'm already having the data in that format. And as you probably all know, NumPy has these standard math operations that I was doing on individual values defined also for vectors. So I can actually do the minus and the square on the entire array. I can sum it and divide it, and then return the square mean. So I can define this function which does the same thing, and I can time it again. And now let's see if that helped. So I'm using time it again to run a couple times. And hopefully, I'm now looking at 10 milliseconds. And if you remember, that's actually a very good improvement because we were at 1.3 seconds before. So this is a great improvement. It's typically a kind of orders of magnitude improvement if the original code was really bad. I can look at the timing again using the line profiler. I can see that most of the time is now being spent in this expression, and there's some time being spent in the mean. So I could continue this and see if there are faster ways for these expressions. And one way to do that is to use code compilation. So you may have heard everyone here uses Python, but there are other languages. We're not supposed to talk about them in this conference, but they have some advantages, and some of them are faster. Languages like C, C++, or Java are faster, and they're faster for a reason that they're compiled. That is, they're actually translated into machine code, and when then computer runs them, they execute much faster. We can reap some of those benefits in Python still with tools like Numba, which lets us compile parts of the Python code which otherwise is not compiled to machine instructions. The way you could do that is to add this magic almost decorator to the function. So the function is exactly the same as before, but I'm adding this njit add number njit decorator to it. Njit stands for just-in-time compilation, which means it's going to get compiled the first time I'm going to use it. And N stands for no Python, which I'm going to recommend as the default. There actually is a JIT decorator as well, which is what you will most commonly find in the documentation. But it has this tricky behavior that if you put something in the code that number cannot compile, it will default to just running Python. It won't necessarily tell you, and it will just be very slow, and you will not know why. So people use JIT with an option called no Python. Oh, apologies. Live coding.
You missed the P.
Yeah. But if you get, if you don't want to type this all the time, you can just do njit, which is the same. So what this is going to do, it's going to take this function and compile it the first time I run it. So if I want to try it now, I'm going to use the time so that it runs only once. And actually, it wasn't terribly slow, but it's not what I'm looking for here. But the next time I'm going to call it, and I'm going to use time it for that, it should be much faster. So let's look at that. So now I'm at 5.96 milliseconds. So let's compare that to this version. That was 10. So I got the runtime even further down by compiling the code that was previously already fast. Should we do it everywhere? Should we use number for everything? Well, it turns out we can't. It's only a subset of Python that can work this way. Most of just regular Python code will work. Most of NumPy operations will work. But for example, operations on pandas data frames will not work. There's a project by Intel called SDC, previously HPAT, that focuses on that is covering pandas the same way. But if you're operating on NumPy arrays or just using regular Python operations, this can make a big difference. But I'm also losing certain things because the code is now compiled. I cannot use some of the benefits and flexibility that Python gives. For example, I can no longer use the line profiler because Python does no longer see line-by-line execution. These are machine instructions that are a little bit cryptic to anyone who wants to look at it. Also, things like debugger would not work in this case. And I can compare this against code that someone else wrote and optimized. So in the stats models library, there's a RMSE implementation. I can time that. And let's see how we did that compared to that implementation. And 10 milliseconds. So it's not the best time. The best was actually this compiled. But it's probably still my best choice because this is a function that someone else wrote, so I don't have to write that code. It would have tests, it would have much better documentation, and it probably will cover some edge cases that I haven't thought about, which my naive few line implementation here would not process correctly. So after all this, I would probably conclude that actually my best bet is to use this function that someone else wrote, but at least I know that it's relatively optimal. And we have about 5 minutes left, so I'll flip back to Stanley and to bring us to the conclusion. And if you have any questions, please fire away, and we can stay around a little longer as well.
Yeah, so I think actually if you go and look at the GitHub repository, we actually have property-based testing as well. I think there's an exercise on that. I would encourage you to go and look at that too. But just to quickly summarize what we've just discussed here. So for performance, like we mentioned, you should always make sure obviously your code works first before you try and optimize performance. You can use magics like time and time it to go and determine how long it runs. Then you can use profiler to see where's the bottlenecks, and then you should use optimized methods that's out there to try and optimize your code, and then only use things like number to try and solve your or to make your code more optimal. So we've also provided some good links there. You can go and look at some talks and tutorials to dig in deeper. So we actually want to conclude with just bringing everything together quickly, and there's like 4 key things that I would want you really to walk away with. We've said a lot of things, but the first thing is, and this might be a bit controversial, but I do believe in this, and we believe in this a lot, is you have to write programs for people, not computers. And the reason for that is if you want your code to be used, people need to understand it. And a lot of what we mentioned, reproducibility, code quality, putting comments in your code, making tests, all of that provides trust, and also people will then start using that, right? The second point would be make it readable, reusable, and testable. Make your code, just look at all of those three components, and then optimize so only after you've found that something works. And then the last thing would be, obviously, and this actually collaborating and sharing knowledge helps with improving your code. If you have more people working on your projects, more eyes looking at the code itself, the better it's going to be. So that'll be how we conclude. And if there's any questions, please let us know. So yeah, we'll just open for questions now. I think we have about 3 minutes for questions, if there are any.
Do you guys really strive for 100% code coverage? Because I always have the trade-off between what to test, and then because the testing itself is code that has to be maintained.
Yeah.
So the question is, should you strive for 100% code coverage? And it's actually a little bit of a controversial topic. 100% turns out to be actually a misleading, kind of a false target. You can have 100% coverage and still have lots of bugs in your code. So what you should strive for, I think, is kind of a non-decreasing trend in your code coverage. So when you're adding code, you're also adding the tests. But rather than aiming for 100%, I think it's better to spend that time in deploying other tools that can check other aspects of the code, such as Pylint that checks the quality and the naming and the readability, but also things that actually make your tests more powerful, like hypothesis. Unfortunately, we didn't have time to dig into that, but our repo has that exercise. You can look into solutions. It will be number 6. It has a brief explanation and a demo you can run. Hypothesis in just few sentences would be a tool you can use to generate the various use cases. You remember in our example, we had to enumerate these different latitude and longitude combinations. Hypothesis lets you is kind of your test engineer that generates these for you based on some predefined specifications. So you would say what kind of numbers you're going to work with and what assumptions you're making about the results, and it will generate you a ton of use cases and explore all the corner cases that you would not think of. And that's much more valuable than 100% code coverage, because it's actually in-depth testing of all the dark corners of your code that would not come out otherwise. There was another question.
I have a question on how you organize the architecture of where you're writing and storing all your different modules and functions. So one issue that I constantly run into when reading other people's code is trying to follow the logic of the flow. I don't know if you guys have any best practice recommendations. Do you like to structure it in terms of like the logical flow through of the actual code you're running, or from the bottom to like the highest level, or what do you have?
Yeah, I think this is hard. So the question was, how do you structure your code? How do you keep it understandable in terms of what the workflow looks like? And you're not alone. There is this is major topic that everyone struggles with. There's also a very good XKCD comic on how do you understand other people's code. There's these bizarre places a person gets to that has no understanding what they mean, and I think there's always going to be a challenge. But you can simplify things by breaking things down into logical modular units, right? So we've just used a few files here, but in a larger project, you would have more similar parsing tools. You would have some testing tools. You want to organize them by topic. Make sure that the contracts that these things declare in terms of inputs and what they do are meaningful, that their documentation, and kind of decompose things into chunks that are small enough to be understandable. Anything that's going to be large and complex will always going to be difficult. So just breaking things down into hierarchies and reusing things is what we try to do. There were some tutorials on packaging. So rather than having like one big blob of code and repository of everything, packaging things into smaller components is an answer. And there are techniques in Python that we did not explore here, but that lets you do that. And I think you can see that in the open source ecosystem. You're kind of pulling these single or multiple use tools together effectively. Imagine just having to write all that yourself.
Do you have any tools for visualization? Like, are there any tools out there for visualizing the hierarchical structure of these?
Yes. So there's a tool. There's a tool for generating documentation called Sphinx, Sphinx, what that would do is it would look at your code, and you remember we had these doc strings at the beginning of the function or a model. It would extract those and generate like a readable documentation from that, plus any text you write on top of it. Any open source project that you would have seen on this conference pretty much uses that to generate the documentations. If you go to read the docs for pandas or whatever, you will find documentation that was generated that way. And one of the plugins to that tool is a module dependency. So it literally generates what you just said, a graph of module to module dependency, so you can see what depends on what. And if it gets very complex, that's the time to refactor.
Thank you.
Question?
Sorry, just for number, so number one, does it affect, by having it enabled, does it prevent that code from being debuggable? That's one, and if that's true, is there a way where you can have like a debug release mode, meaning for like debugging testing purposes, I'll have my code randomly get disabled, and there's like some like global flag I can have it enabled, so that way when I release it in production, I get the purpose that I want.
Yeah, so the question is, if you use Numba, does it prevent debugging? And if so, can you manage that by having like a version for debugging, version for production? So short answer, yes, it does prevent debugging. It compiles it to an LLVM representation, which you can't inspect in Python. There are probably some tools you can use still, but they're much more low level. That would not be Python debugger anymore. But since it's just a Python decorator, you can use it flexibly. You can turn it off programmatically based on options, right? That's kind of up to you, but it certainly can be an option you introduce in your code base. I'm not aware of some kind of a global switch for that, but since it's just Python code on top of your function, you can do whatever you want with it. All right, I guess the last question.
Yes, kind of a selfish question here. So I'm trying to contribute to an open source project, and there's one file. It's a relatively small package. There's only a few people working on it. There's one file. It's only 2,000 lines long, and I'm making a minor change. But I mean, I have a hard time figuring out where to put my code relative to the file. I mean, I'm trying to figure out how it's organized, and I can't figure out how it's organized. Like whether functions that are just called the same thing are grouped together, or maybe there's a main function at the bottom. Doesn't seem so. Or like there's like important ones at the top or at the bottom. I mean, those are the two things I thought of. And then I'll try to see, okay, which ones is inputs and outputs to the function.
Right. Yeah. So the question is, you're trying to contribute to an open source project, but you can't really find your way around. You don't know how the code works, and there may be no tests also. So you should tell the author to watch our tutorial because
the zero tests.
Yeah.
I was thinking about contributing it to my first test, but it's a very small change. So what would be the first couple of things that you would look at?
I think as the maintainer of that package, right, I would want to see tests for your change, right? First, that all the existing tests work, and then any new tests that you've written also work. Right?
No tests.
Well, so you probably want to walk away and contribute to a different open source package, or write the tests. All right, I think we have to wrap up. Thank you very much. I hope you enjoyed this. Thank you.